video, so I don't intend to go over the entire thing. But this is a two-phase system, and if you look here, it's 120 volt on the top half, 120 volt on the bottom half. That's how you get your 240 volt in total. So my multimeter would be between here and here to get the 240 volt. And I believe that's the homework question as well. Just can I borrow your homework?
Sure.
And it's, sorry, Jasmine or
Yeah.
Jasmine?
Oh, yeah. Jasmine.
Jasmine. So the homework question, problem number 4, is a 120 240 volt AC. This is how you get your 120, either 120 or a 240 if you combine. What I did in the class is I assigned an IA and an IB, and I gave it a 7 amp followed by a cosine something, a 7 amp followed by a cosine. This 180 degree was to counter the fact that this IB is going in the opposite direction. And then, because you have a cosine theta, let's just assign this as theta, plus pi, your trig identity should tell you that cosine theta plus pi is negative cosine theta, which means IA and IB in the neutral. So why I have done this IA plus IB, that's the neutral. So IB flows through here, IA flows through here, your neutral is 0. So your first harmonic, so to say, 60 Hertz, leads to a 0 current in the neutral if it's a balanced loop, and I used a balanced ZL and ZL. I then skipped and used I then considered a non-linear load where I used 7A and I still had the 60 Hertz, a 4 ampere for the 120 Hertz. And how I did the 120 Hertz is 2 times 160. And I did my third harmonic, which is 3 times 160, and I added a smaller current 1.5. I did the same for IB, but I added a 180 degree to counter for the fact that the current is in the opposite direction. And I already proved IA plus IB, the first harmonic, in the previous page. So I didn't do IA plus IB for 60 Hertz. I skipped ahead and did the third harmonic just so that I can prove that the odd ones lead to a 0 current in the neutral. Now this you have to be careful. This is different from a 3-phase where the third harmonics is what, the odd ones is what you have to be careful, what shows up. So in a 3-phase or even on the 9th, you only have the odd ones, 1, 3, 5, 7, and 9. Keep this in mind. I think it's so simple enough that you guys are going to confuse it, and if you haven't looked at it throughout the weekend, I think you should start looking into it. High probability, it's already in the homework, so high probability for an exam as well. So in a 3-phase, it's the first 1, 3, 5, 7, and 9 that show up on the line, not on the neutral. And on the neutral, you have to not only look for a 3N, but also need to look for the odd. So it's the neutrals will only have the third, the 9th. Should probably write 15. 18 doesn't show up, but 21. But on an exam, on homework, it's tough enough to reach 10 harmonics. This is kind of like a silly thing. But if I ask you for the line current, you have to consider 1, 3, 5, 7, 9. If I ask you for the neutral, you have to consider only the third and the 9th. In this 2-phase system, on the other hand, you will find all the current showing up in the line, which is what I'm showing here. You have the first harmonic, the second, the third. I didn't bother to do all the 8. I just showed a few, and then it was more of a pattern for me. So in the neutral, only the even ones show up. So 1 and 3 cancel out. So 2, 4, 6, and 8 show up on the neutral. So just keep that in mind. And I believe this is your homework number 4. I guess this is pretty simple to find the TST. Any questions on the TST? This one up? Yeah.
About that, I still had a question. So for the three-phase, when I'm not worried about the neutral, I have to remember the odd triplets.
You're not worried about the neutral.
So you would have, when you're not worried about the neutral, you worry about 3, 9, 15, and 21. Or
No.
I just missed that section on the three-phase.
If he asks for line, you do all the numbers.
Imagine you have a YY system. Here's your Y source, here's your Y load. Now this is a three-phase system, right? You have a pick your like A, B, C. So you have three sources, A, B, B, C. And you have three nodes, A, B, C. What's happening is, because these are non-linear nodes, which means there's a capacitive or some sort of an inductive here, there is going to be a harmonic distortion. So if you have a harmonic distortion, you're not going to have just a current, you are going to have several currents flowing through the line. So if I want to find the line current that's here, I will have to do 105 square, 80 square, 15, 40 square, 30 square. And I regret writing so many numbers, but yeah. So you'll have to do all of this to find your line current, right, and square. Question is what happens in the neutral. Now if I want to find the neutral, I should take the triplets. What are triplets? Triplets are 3, 6, 9, like it's 3n odd. But what you have to keep in mind is for the neutral, you not only have to do 3n, but also make sure that you're picking up only the odd numbers. So 3, 9, 15, 21. Easy example is 12. 12 is a multiple of 3, right? But it's not an odd number. So to find the neutral, all you have to do is set 80 square plus 30 square. And this is wrong. Tell me why this is wrong.
Times 3.
Yeah. Don't forget that. It's 3 times triplets. Why is it 3 times triplets? Because I just showed you just the line current. For what line? Let's say this is C. So this is line, just the C. There is the same current happening in A, same current happening in B. So you have to consider 3 times the triplet currents for 3-phase. It's simple enough that I am at this point willing to take away half your points if you don't show me 3 times. And it's a conceptual thing. Like line current, I get it. Okay, this is my line current. But think of this in a way. This neutral is connected to all the 3. So I have to actually add up what's coming from A, B, and C. So it's 3 times the triplet.
Whenever we're solving like a homework problem, we should always make sure we're solving for the harmonics on lines as well, or will you guys tell us when you want us to do harmonics on the line curve, or always?
So there are only few questions that I can ask you on this. One is tell me the line current, tell me the neutral current. The next is tell me what the TST is, right? There's not a whole lot that I can ask you on this. So what would your TST be? sum of, yeah,
Like the square root
Uh-huh.
of everything after one, like.
Right. yeah, so
Number
from
two
2
plus-
to everything else.
Yeah, and then that divided by the first one.
Yeah, so your THD, and it doesn't matter whether it's current or voltage. It's sigma, and keep in mind, I was going through some textbooks, some use N, some use H, probably to show harmonics. Doesn't matter what the alphabet is, but N is equal to 2 to infinity of, I'm just going with the currents for the time being, square divided by I1 RMS. Well, it's always going to be RMS, but. So what that means is to find my THD, all I have to do is, do not consider this 105. 105 here. Everything after the 105 would pop here, and your 105 comes here, and then you get a THD. And if I do not give you a THDV, assume it to be 0.
For the two phase, do we follow the same idea? Just everything after one and then that divided by.
So I gave you, I gave you the what shows up in the neutral. I want you to work whether it is 3 times, 4 times, or 5 times. But that should be. Hold on. Maybe mute. So in a 3-phase, I showed you how it's 3 times because you have 3 legs, so to say. I'm sorry, this is bad. How about in a 2-phase? I mean, you have an IA flowing and an IB flowing in here, but it's only the 2nd, 4th, and 6th. So essentially, rather than doing, shouldn't be saying this, essentially doing rather than 3 times the currents that you are concerned with, do 2 times the current because there are only 2 currents coming in. You get it?
Yeah.
Okay, here a few yes. You guys getting the concept what I'm trying to say here?
Yep.
Like why I'm not bothered by multiplying it by 3, but rather 2.
Okay, and then that's for the line current.
No. The line current is line current, everything just shows up. Think about this. The line current is 7A, 4A. So the line current is 7A, 4A, 1.5A. When I looked at the neutral, the third ones, the odd ones, so the 3, 6, 9, all of them are cancelling out in a 2-phase. Similarly, the first harmonic, that is 7A cosine 60 Hertz and 7A cosine 60 Hertz plus 180 is cancelling out because of this trig ID. Cosine of theta plus pi is negative cosine theta, which means the first one and the second one are just cancelling themselves out in the neutral. But they do produce themselves from a line. So the lines you have to consider similar to, okay, for the lines you have to consider everything, 1 through 9 or whatever number they throw at you.
So then on the 2-phase, it's pretty much like all the evens will cancel each other out and all you will have left.
No, the even stay.
Even stay.
Yeah.
Okay.
So that's, I think, that's what's tripping most of the folks. Or any current that I give you should show up on the line. Like there's no escape from it. If I give you a current, where is it going to escape? It's when this IA and IB meet this point, it may or may not cancel each other out. And in case of a 2-phase, the even ones stay, all the odd ones cancel out. So this is the first harmonic. Let's just consider this guy once more. 7 ampere cosine 60 Hertz, 7 ampere cosine 60 Hertz plus 180. 180 is just to show current is, if I take clockwise as positive, just to show anti-clockwise. And cosine of some angle plus 180 is equal to negative cosine theta. So this, if I add to this, essentially means I'm subtracting both the currents. So IA plus IB, in case of, I should have put a 1 here, the neutral is 0. And that's only for the first current. What happens if I keep, not first current, the first harmonic? What happens if I keep adding the second harmonic, the third, the fourth, the fifth? The pattern that emerges is the odd ones, same deal. The moment you add 180, it cancels itself out. And what happens in the second is, it's 2 times 180. Can you see that? Because I'm trying to get 120 hertz here. So it's 2 times 60, which is your 120 hertz, and it's 2 times 180, which is essentially 360. So I have 2 currents going in the same direction. Same direction as, because it's 360, it is as good as adding a 0. So I end up with 4A cosine, whatever is this, plus 4A cosine, and this 180 doesn't do anything. It's literally the same current. And I end up with 8A blah blah blah. So that's my thing. And then, see this? I double the current. So that's what I'm saying, you have to double the current, not triple. It's double the current. Having said that, when you look at the RMS of 8 ampere, you end up with 5.7 amps in the neutral. So in the neutral, I only have an even current. I take the V max of this, divide by √2, I get 5.7 amps. And the line currents is what I did here. IA1 RMS, IB1 RMS. So it was 7, 5, and 1.5, and I did √2 to make it into RMS. And what did I end up with? 5.8 amps. In other words, the neutral and the RMS effectively are almost the same current. Now this is considering that only there was 1, 2, and 3 harmonics. You could have more, but typically and that's your homework problem. Like they made a whole bunch of other currents. But in reality, I would say it's like 1, 2, 3, maybe 4, not more than that. But in the homework problem, they went all the way to 9. So you will have to find whatever neutral currents you think is right, which I just told you is the even ones, but keep in mind you have to double it. So it's, but when I say double, it's
Multiply them
give me a second. Wait. No, hold on. When I say double, just don't do 2 times something, you have to do this guy. So it's root of all the even ones. So under that root, 90 would be there, 75, 45, 35. And then keep in mind, you have to multiply by 2 also. Mario, does that answer your question?
Yes.
Okay. I have a bad feeling this would be the first class that's going to get a very high score on homeworks. Normally we don't discuss homeworks.
Bad feeling?
Yeah.
Good feeling?
I mean, it's going to be like, I don't know, since 2000 homeworks is an average, and then spring 2024. Good.
Oh, don't worry, I do horrible on tests. They'll even out.
I'll do better on that.
All right. Honestly, I think I need to get going on the next topic. So the topic today is this guy, per unit and single line diagrams. Let's see how much we can cover. I thought we should be able to cover, but we sort of had to discuss homeworks in 20 minutes out. So all right, we have at this point seen a few one-line diagrams, but I thought I should give you a formal one-line diagram that's going to cover more or less everything that we are going to encounter in 347 and possibly a bit in 348 as well. So looks like I told you, you should always keep your SI units along with the answer, but you forgot to put boxes, is what I heard, on your answers, so
Some teachers like them, some
Yeah.
teachers don't.
anyways.
Yeah.
It was interesting, I thought I had covered everything, but I still didn't.
Oh.
So anyways, today we are going to look at per unit representation and one-line diagram. I thought we should start with a one-line diagram and then build our way to the per unit thingy. So these are the different components and equipment that I want to see on a one-line diagram. I want to see one generator which is at 50 MVA and it's able to produce 24.6 volt. I want to see a transformer which is going to step up 24.6 kV to 56 kV. And this GSU should have been here. It's a generational step-up transformer. They just call it GSU. Distribution guys want to call their transformer as distribution. Substation guys want to call their transformer as power transformers. Generator folks want to call their transformers as GSU. And right after the transformer, I want to see a 56 kV T line is what they call. It's actually T is for transmission. And after it starts to transmit, because I'm taking it for very long distances, keep in mind it's like several hundred miles, I want another transformer to step it up from 56 kV to 150 kV. So all that I'm trying to do is produce that 24, stepped it up to 56, then I'm again stepping it up to 115. And once it reaches a substation like Beaverton, Hillsborough, Gresham, Salem, wherever, I want to step it down from 115 to 13.2. This side of the river, it's always 12.47, but 13.2 is sort of understood across US, so I went to 13.2. And then I have 3 loads. This portion you guys have seen in your first homework, so I'm not going to spend a whole lot of time. You have 3 loads, 3 voltages, and 3 MVAs were given. I didn't add power factor, but you might as well add power factors if you want. So how do we go about it? So,
If you change the HDMI, you'll be able to
yeah.
turn off the screen. Ah.
Nice. Hopefully I did an EV mute. So I started off with a generator. Either one works, and this is one symbol that I like to use. The other symbol that I've seen happening is this guy, just to show the rotor. Doesn't matter what you use, but just saying. And then it hits a transformer. This is how I like to see a transformer. There is another way to show a transformer, that is yay. And this is stop. Like, I haven't seen this being used in a while, but I do see it in some low voltage guys still using this. So there you go. Let's have it. After that, this was at, I don't have to say this is 3-phase, but let's do it. 24.6 kV. And this is part of your homework. You have to draw one line in Power World and solve it. So part of this class, as of now, you should be good to draw one line, and then it's just button clicking in Power World and it'll throw you some results. You don't have to know that results as of now. End of this term, that should start making sense for you. For the transformer, I don't care what you put here, what you don't, but always mention the voltages that's on this side and this side. And how you do that is 24.6. And kV, I use 56 kV. 56 kV. Now when you're doing in CAD, there are several folks who are very particular that the 24.6 should be on this half and 56 is on this side. But I'm just drawing it right now using a dry erase, so bear with it. And now here I have a bus. I can add as many T lines or transmission lines. This is my generator, a dam, nuclear, whatever you want to call it. From there, I was able to produce a low 24.6 kV. And I stepped it up to 56 kV. And this is my so-called bus 1 or B1. And here I can add as many transmission lines that I want. I am adding only one transmission line. Typically we show it using just a straight line, but for the purpose of this class, and just to be, just as a trailer into what's coming your way, a transmission line is typically shown using a resistor and an inductor. But you can get away using just a straight line for the time being. And the reason you can get away I then have to step it up to 115 kV because it's going across the border to California, Washington, or wherever you want to take it. And the reason I want to step it up is because higher the voltage, it's cheaper to transmit. Less is your losses. Now you could argue, hey, I squared R losses, yeah. I want to produce as little current as I can so that I can reduce my I squared R losses during my transmission. So what I do is I pump up my voltage. So here, it's 56 kV here. And this slanting line tells me that it is getting transformed to 115 kV. And again, here's my giant transmission line. Just for the sake of it, and so that you guys see this is 56 kV. Well, actually, it's 56 kV all the way to the transformer, right? And from this side of the transformer, it's 115 kV. So 115 kV is 115, so many volts. So anytime I want to put a transformer, we would prefer to have a bus and then put a transformer. The reason is, if I want, at this junction, I want both 56 and a 115 kV. It's easy for me to see that this entire node is 56. So maybe there is a client, I don't know, Daimler who wants 56 kV, Intel wants 56 kV. And then I have another client somewhere here who wants only 115 kV. So I can just tap it off this bus. A few things, those who are aware of this system as such, I haven't put in breakers. Truth be told, there should be a breaker on this side, like there should be several breakers all over the place. Because if one of this, think of this, if one of this line has a fault, now I have to take down the entire system. Now this entire system could be Oregon or Washington. We don't want to do that. So what we do is we put breakers on either end, and we just open up this line, so to say. So the rest of the system is still working. So it's 115. Come here again. Here I'm stepping it down to 13.2 kV. And at this bus, This is my bus 4. I think I had 3 loads. But before the load, I added a transformer. Starting here, it's all 13. All right. Now the brilliant idea here, I mean, once you see it, you're like, yeah, not a big deal. You have 56 kV. Let's say this is, I don't know, just maybe over again. This is OR. There's 56 kV, right? Imagine this to be again or again. 115 kV, you're taking it all the way to Washington, for example. Now, a lot of things can go bad in between, and you just have one generator. If your generator is gone, you're kind of, there's nothing else to do. You just have to bring it down, which is why you have different generators. You could have a nuclear, you could have a hydro, you could have a thermal, all that. Right here at this 56 kV, I could do what is called a tap. Where's my 56? Yeah, I could do it here. Does it work? All right, guys. I could take this 56 kV to, I don't know, I'm just making stuff up right now, like to Hillsborough maybe, or to a client. So these nodes where this thing happens is typically in a substation. So that's where you tap off a lot of, and that's one reason at a substation you're going to see way too many circuits coming out. So from this position I could also do, just because the Beaverton is close by. And on this, I'm not sure what the cities are, but let's try it. Seattle maybe. What's one close to Redmond?
Centralia.
Nah, I don't want to write that much.
Okay.
I don't know. Redmond maybe?
Olympia.
Olympia, right?
Yeah. We know what you mean though. It's other places in Washington, traveling far.
Now I could add, easily have added from here or from here another bus and another transformer and created a different system altogether. And this system is so interconnected that after a while you're like, oh my god, I don't know what I'm looking at. I mean, I can see a power flow, but I just added a voltage here. The transformer not only has voltages, but MVAs, impedances, like so much information comes up. You're like, I need to find an easy way to take all this in. And that's where per unit comes into play. So per unit is a way where you normalize the values. You don't take away any of the values, you just normalize it. And the way I think of per unit, maybe you need this. in case you want it for your notes. I have a, oh yeah, sure.
It's the same.
Have you guys heard of, I'm pretty sure you guys have heard of PPP index, right? Purchasing Power Index? Yeah, okay. Anyone here has heard of Big Mac Index? Or KFC Index? Alright. Imagine this, and I'm just trying to explain it in some way so that you graduate, you are done, but someone talks about per unit and you need to understand this. Don't put this because it's embarrassing, I don't know what to say. But anyways, Big Mac Index, I believe it was in late 80s that the magazine Economist came out with a Big Mac Index. What they're trying to do is the price of one Big Mac in every country. So that it tells you, you know what a Big Mac looks like, feels like, right? And most folks have eaten here in US. Once you move out of North America and Europe, it's kind of just coming up. But Big Mac is one product that's available all across. So what they've done is, price of a Big Mac here in US, around $5. What's the price in Switzerland? What's the price in Liechtenstein, for example, or Germany, or India, or China? And that gives you some sort of an idea of this currency exchange and some kind of purchasing power that people have. So the same product, I believe it's $5.5 or something, but if you take it to India, it's like $2.50. And I did see something which was even less than that. So that, in a way, you just solve the entire world's currency exchange and economics using Big Mac. The same deal here. I said it, you forget it, I shouldn't see it in your notes. I had an embarrassing presentation for it, but I was like, nah. Someone's going to show it tomorrow, and I'm like, no way. So this entire system, now we have way too many numbers happening here. What we do is, we are going to normalize, and it's actually dumb math, but the more you get into it, you are going to lose track of which is what. So I'm going to go a bit slow, and for the rest of the day, that's all that I'm going to do. There are two places that PU can be, we call it per unit, can be brought into a lecture. One is just before we start teaching transformers, or not teaching, that's a strong word, but just before I can discuss transformers, or the T lines. In our syllabus, it shows up today, but when I was looking through the previous notes, including me, it was shown up during T lines. But I just want to keep the same syllabus and not run into trouble. Plus, I don't look into your labs and homeworks that much. So I thought, you know what, I'm just going to keep the syllabus as it is. So we are going to look at per unit and see how that sort of helps. And the beauty of per unit comes in when you're doing big systems. When you're doing small systems, you're not going to have that sort of appreciation. Once you do very big systems, you're going to run into the same issue that I mentioned. A Big Mac costs so much here, a car costs a different price, a house costs a different price. Think of this, this is a house, this is your Big Mac, I don't know what this item, but make it up, a car. Now all these numbers are floating around, and this is just Oregon and Washington. What happens when I bring in California, Texas, Nevada, like, it's going to get crazy pretty soon. So we normalize everything to one number, and that's called a per unit. So, there are three big advantages that I just sort of wrote down, which I feel are the big three advantages that happen with per unit. One is next week we are going to look at something called a transformer equivalent circuit, and that can really be simplified using per units. Rather than going back and forth between, you know, impedances and voltages and different systems, once you put it to per unit, it simplifies your equivalent circuit. And then the other one is, it helps you in avoiding very serious calculation errors. Think of this. There could be several calculation errors just in this. Now if I keep on adding system, it's very hard to figure out where exactly I made a mistake, and even if I made a mistake. So per unit helps you catching those serious mistakes pretty quickly. It should be common sense that if something is costing, let's say $5 here, Switzerland is going to cost more. Thailand and India is going to cost less. So that kind of gross errors can be quickly caught when you are doing it per unit. Last but not least, impedance of similar type equipment within a narrow numerical range. What this means is, if I have a transformer, and if I have another transformer with more or less the same voltage, if I do a per unit, it's going to be within a range. I cannot get a value, let's say, I'm just making up this value, let's say I get a per unit of 0.9 here. I definitely cannot get 0.1 for the same transformer at a different part of the system. It should be in and around 0.9. I mean, there are going to be changes, but it's not going to be a big change. Yeah, if you want, you guys can take a picture of this. Not that important, but I just wanted to bring it. And before I get too far ahead, were you guys able to find Sherman Glover or the Chapman textbook? Show of hands who doesn't have a textbook as of now.
Who does?
Have to start
Who
reading
does
it.
not have a textbook, either a PDF or
I haven't found it, like, I found those
Sorry.
couple.
You were raising your hand or not? So you have some sort of a textbook with you?
7th edition, right?
You have a PDF?
Yeah,
Okay.
pretty sure.
It's 7th edition, right?
It doesn't matter, whatever you have.
Yeah.
Okay.
Sorry, Alan? Alan, right?
Yes.
Yeah.
I was just gonna say, like, I tried to use it early on in the class, and it wasn't as helpful as I was hoping it was. So
Okay.
I don't know.
The chapter.
Oh, maybe I don't have the chat.
No, Glover is good enough. You start off with Chapman and then you move yourself to Glover, that's what happens. But, yeah.
One thing that I noticed is that it follows the international version instead of the regular one.
It doesn't matter.
There's chapters on the regular one there's chapters in the international part and the international version that the regular one doesn't have.
The regular one doesn't have and the international one has it?
Yes.
Oh, nice. Which one? What chapter?
The 5th version of the book.
Yeah, I have the
has
5th version.
7
Do you know what chapter it is?
There is about 7 chapters in the regular one, and there's about like 12 chapters on the international version. Yeah.
That's weird.
Yeah, I just went with my.
Appreciate you. I'm first.
Yeah, good, fine. Oh, you're fine. I guess I found a different one. Was-
No, this is an international
That's
one.
it, yeah, that's the
Oh,
one I have.
Yeah, that's the one
Oh,
I have.
sorry. It's
But
an
if you go into
international.
the regular one, I guess, take you North American
That,
version.
there could be a reason I did see there was the older versions where they split the chapters.
No, it was the 5th version as well.
Was it the 5th one? Oh,
Yeah.
No idea. I think all of us just went ahead and used the international version.
Huh.
The regular one, for some reason, it's pretty costly.
Costly.
That's the one that's sitting in the Power Lab.
The
So-
regular. no,
The international version
Oh.
is the one sitting on the table, so anyone can read it.
All right.
Like-
So,
it's just better
like
to
I
read.
said, the math is not that hard. All you have to understand is per unit quantity, and this doesn't matter what textbook you use, this is it. It's the actual quantity divided by the base value quantity, and we will get to what the actual quantity and the base value quantity is. The actual quantity is the quantity that you are concerned with at this moment. So for example, if I'm concerned with, keep this in the- So for example, if my actual quantity that I'm concerned with is 18, let's say 18 kilovolt, or it's an equipment specification, that's my actual quantity that I'm concerned with. The second quantity that I have up in the screen is a base quantity. this is a value that I choose. Looking at the system, I will choose a value that's going to be my base quantity. So, for example, I'm going to choose 20 kilovolts as my base. So my per unit, and I'm just going to call it PU, is my actual, which is 18 kilovolts, divided by my base, which is 20. And I believe this is 0.9. Right? This is 0.9. Yeah. That's published. Can you guys see this, what I just wrote? Okay. Now what happened here is, my base quantity is something that I will always keep in my memory inside my wallet. I just know the entire system is based, not the entire system. Part of the system is based off on 20 kilovolts. Now, anytime someone talks to me about, hey, I looked at an equipment and it's 0.9 PU, that gives me a sort of understanding, oh yeah, that works, that's within margin. And you guys have seen this PU being mentioned when I was talking about lag and sag. Or when there is harmonics, there is a chance that your voltage might try to sag between 0.9 less than volt less than, I believe it is. So this is the PU that I kept on trying to say. So in simple words, I choose a base, and then whatever voltage comes my way, I just put the actual on the top, divided by the base, and there comes my PU. And that tells me, okay, how good it is, how bad it is. Now, when we were discussing power quality also, this is sag. I was talking about swell, where you had the voltage going, I believe it was 1.9 voltage. I don't know, at this point I'm probably looking this up. 1.8 PU, which means I have some sort of a base voltage, and from there 80 times higher, 1.8, so 80% higher or 10% higher, both are going to be a swell voltage. If you have still not got it, it's fine. I'm just going through the motions right now. We will do an example, and there's a lot of stuff coming your way. But the basic at the heart of this is per unit is actual quantity divided by base value of a quantity. Base value, you choose a value for a quantity as your base, and it's always a real number. Keep forgetting that. When you choose your base quantity, never add an angle here, because you don't want to take away that information. The angle information, whatever is with your actual quantity stays. Your base quantity is just a real integer, there is no angle associated with it. And because it's a ratio of the same kind of quantity, PU is always going to be dimensionless. So I don't want to see a 1.0 PU volt, and I think I made, oh, thank God I did. I was about to write a volt here, but it should always be a PU. It's never PU volts. I did mention a volt here so that you know what I'm talking about. Still going ahead with stuff, and once I show you the example, it will start clicking. In a PU system, there are 4 things that you are actually looking for. The first is your apparent, second is your voltage, third is your current, and fourth is your Z, so impedance. Keep in mind again, in PU, S, V, I, Z not represented with SI units. So once you're in the PU system, it's just a ratio. Now how do you choose your bases? So let me just skim this for a minute. So I told you that you get to choose your base. So how do I go about choosing my base? So the first thing, Did you see my red? Oh, yeah, there you go. The first thing is you have to choose an S. I think I'm going to take away some stuff from here. So you have to choose your base values. Now, you can pretty much choose any value as your base value. I'm just making this up as. I have a bad feeling I'm not doing something right with these. They just go right. Should I be keeping this closed? Maybe?
Shouldn't go right that fast.
Things that I don't know. Can you guys see this 50 MVA? The sad 50 MVA. Even this is good. So the bases that you have to choose are S base, a V base, an I base, a Z base. You guys get to choose what your base what you typically want. 95% of the time you pick the generator's base for the S value, and that's used throughout the system. So no matter where you are, you don't choose your, see this MVAs here? It should be MVA. You could choose this, but you are going to create a lot of trouble for yourself. So try to go on the higher side, like where there's generation, and pick the highest MVA. And the reason for that is once you build your system, tomorrow if your client is shutting down his business, that's gone. You'll have to redo the entire system. And you don't want to do that. Whereas this, 60, 70 years and it's still working. So you're good with having this guy as your base. So always try and choose an S base that's more on the generation side. So just for the sake of it, I'm choosing 50 MVA here. The voltage base is actually dependent on where you are looking at. So I kind of mentioned, but I didn't pay much attention to it but then. This side of, oh yeah, I did show 56 kV, but it should extend all the way here, right? Anything that's happening on this side of the transformer, I will pick up 24.6 kV as my V base for this section. 50 MVA throughout the system. The V base I pick depending on where I am. So if I'm discussing about something between A and here, my V base would be 56 kV. If I'm discussing something from here to here, my V base would be 115 kV. So you fix these two and then go about your business of figuring out what needs to be done, and that's where all the math comes into play. So we just switch back. Oh, use 50 MVA. So bases are typically S and V, and I just used a 50 MVA as my S base. And just on the generation side, what will happen is when I do my PU, and let me just do the PU for this guy. So, I do SPU. Yeah. Oh, I have it there. Can you guys see this part, or this is, do I need to zoom in? Okay. So I chose S base as 50 MVA. So my PU, and this I just got fancy with my writing. Typically they just put S and a PU, but SPU is my actual quantity divided by my base quantity. Now only for that generator, because that was my base and that happens to be the only generator that I had, the MVAs lined up and I ended up with 1.0 PU. If I had a second generator here, with a 45 MVA, what will happen is, keep in mind, my S base doesn't change for the entire system. It would have been 45 divided by 50, and that would have been a different PU. And I think I had a voltage example where I picked my V base as 20 kV. And let's say there's an equipment that's rated for 18 kV. My VPU would be 18 kV divided by 20 kV, which is 0.9 PU. Again, keep in mind, you have to show voltages here because those are the quantities. But once you do it, or once you go through your math, you end up with just with a ratio, and you call it a PU per unit. So you fix your S, you fix your V, and then you let the rest of it come out of it. What that means is, I did for both single phase and for the three phase. Your I base, keep in mind, these two we picked, we are trying to derive I base now. So your I base is single phase S base divided by voltage, but keep in mind you have to do the line to neutral. Do not do line to line. In that case, you are talking about three phase. Similarly, your Z base can come from V line to N base divided by I base. 9 out of 10, you guys are going to use this formula rather than this formula, and that's the reason I just put it there. The reason I'm telling you that is, remember how you fix the S base and the V base? So it's natural that the Z base should immediately fall from here. In fact, there are several textbooks who talk about S base, V base, and immediately they talk about the Z base rather than the I base. Because it's pretty easy for here to Z right. VLM. Going in the same way, I went ahead and did my I base and Z base for a three-phase system. The only difference is here I'll have to fix my S for a three-phase base and a V line-to-line voltage for a three-phase base. Now I didn't put a three-phase here, so to say, because line-to-line voltage shows up either in a two-phase or a three-phase. We hardly are going to do any two-phase system except for that harmonic thing. So it's a three-phase base, and the textbooks do go by VLL base or some sort of a VL base. So again, your Z base is V line-to-line square base divided by V three-phase base, and your I base is this guy. Now, just to have some sort of a, I wouldn't say an algorithm or something, but I just decided, in case you guys are going to forget all of this and you want to just go step by step and get it out of the way, it's probably one of the only classes that you might be using. If you're sticking with power systems, then of course this is your bread butter daily stuff that you're going to use. So so in a single phase system, pick a VA base for the entire system. So that's SB. Some texts are using SB, but I just call it S1 phase. Followed by that, you pick a voltage for different voltage levels. This simply means you have to figure out where exactly are you in this system. So the MVA is the MVA, that remains there. But you have to decide whether you're on the 24.6 or on the 56 kV side. And you pick a voltage that is line to neutral. And the reason is you're in the single phase. And then you calculate ZB, and then you calculate IB. So pick SB and VB, your bases, and then immediately go and find your ZB and IB. Now this is not a hard and fast rule for your 3 and 4th. You can swap around and do what you want, but I just feel like it should be ZB and then IB. And once you have everything in PU, keep in mind, PU affects your magnitude and not the angles, and PU is unitless. I just called it out here like 1.0 PU and not 1.0 PU volts. This is absolutely wrong. So, for a 3-phase. This is going to get me in trouble, but I still wrote it here. But this is all that you need to know. Same deal for the 3-phase. You are going to do you're going to pick a VA or an S3 phase base for the entire system. And then you're going to pick a voltage for depending on where you are in the system. And here you're going to pick a line to line voltage because you're in the 3-phase system. After which you go figure out your Z impedance and your IB impedance. The only thing that I was hiding here is I used a line to neutral voltage just to be fancy. I converted this VB, and then I was like, am I digging myself into a hole here by putting this? But when you have a line to neutral, it's got to be a Y system. There's no way you have a line to neutral in a delta. But I just called it here as a Y network. So how do you convert your V line to V neutral? It's you √3 and some phase voltage or line to neutral. And how do you convert your 3-phase power to single phase powers? It's 3 times single phase powers, right? You have 3 phases, times 3 gives you the 3-phase SP. And then √3 square is 3, so 3 and 3 cancel off, you end up with this guy. That's more or less the entire thing as far as per unit is concerned. It's not a whole lot. You have a give me a second. Yeah. All that you have is, in reality, is you have a per unit quantity. You have the actual quantity, you divide it by the base quantity. We just looked at how to figure out the base quantity. Don't get confused between PU and base. I've lost a number of times. I have got confused when I was learning this. PU is a unitless quantity. Here, how do you pick your base? You pick your S and your V, depending on where you are in the system. And then you pick your equipment and just start dividing, and out pops your per unit. So, I actually want to do this problem. Why don't we take our break and then come back and hit this problem?